Okay, so let's get started. Today we are glad to have Ignacio Bianchi from University of Republic. He's the recipient of the Frontiers of the Science Award. He will going to talk about the classification theorem for compiled torsional radial in vacuum spacetimes. Let's welcome.
Okay, so thank you very much for the invitation. It's great to be here, and everything has been amazing so far. So, as I was saying, I will talk about a classification theorem for compact Cauchy horizons in vacuum spacetimes, okay? Since I didn't know what kind of public I would have, I decided to split it up in two parts, the entire presentation. First, I will give some context. It will be more hand-wavy, and then I will go into the proof and we'll talk about the details of the proof, okay? So first of all, I would like to give you some context on where we are working. So we are considering time-orientable connected vacuum spacetimes, which are 4 Lorentzian manifolds that satisfy the vacuum Einstein equations that get reduced to reach equals 0. And when we are considering these manifolds, we will call an initial data set a triple sigma gk, where sigma g will be just a Riemannian 3 manifold, and k will be a symmetric covariant 2 tensor that will be basically some kind of extrinsic curvature when we think about it properly inside the spacetime, okay? So when you get this triple sigma gk that satisfies some equations called the vacuum constraint equations, Richard Shane talked about those in his lecture, you get the initial value formulation theorem that's by Choquet, Bruhat, and Geroch that says that any initial data set, when you give it in such a way that it satisfies the constraint equations, there will exist a unique, inextendable, globally hyperbolic spacetime such that sigma will be a space-like Cauchy hypersurface in M, okay? So when you specify this data set, you get a unique spacetime as an evolution of this data set. So the picture you should keep in mind is something like this. Don't think of n as pointing to the direction of time, and it's just a vector that shows you that it's inside the spacetime. You get an initial data set, this evolves by time, and you get a development of the initial data. And there's only one that's maximal, and it will be the unique one, and we will call it the MBCD of the dataset sigma jk, okay? So we get an initial dataset, we evolve it, we have a Lorentzian for manifold now, and the topology will be I times sigma, where I will be an interval. So the problem with this, well, it's not a problem, it's actually what you need to ask for, is that the uniqueness theorem holds in the class of globally hyperbolic spacetimes, okay? Those are not the only Lorentzian manifolds that exist, and it may not hold to be the maximal spacetime among all possible extensions of this data. So what I mean is, if you get an MBCD, you may have an embedding into another vacuum spacetime that's bigger than the first one. So basically, you have here you get sigma gk, and you extend it, and maybe you can actually embed this inside a bigger spacetime later, okay? So the theorem does not say anything about that at all. In this case, the domain of dependence will coincide with the part of the MBCD. You won't see anything behind this or before this. And the boundary here, this region and this region, will be the Cauchy horizon, okay? This is what you call the Cauchy horizon. It's the boundary when you think of it as being inside a bigger spacetime. This Cauchy horizon is actually consisting of two parts, the past and the future components. Any of those may be empty. They both may be empty. It depends on where you are embedding the spacetime, okay? So in order to illustrate this concept, I will talk about a very well-known example, the tau NUT spacetime, which is an interval times S3, where you put an analytic metric that's it has a very explicit expression. I did not want to write it because I won't use it. but it's analytic and it has a lot of symmetries, okay? So you get this very symmetric initial data, and you evolve it, and you find that the tau space alone, without the NUT part, will be an MBCD for this initial data that we will call tau initial data. But the problem will be that this can be extended for time t plus and t minus, just as we said here, okay? And not only can be extended, so you can embed it into a bigger spacetime, but actually, Crucial and Isenberg in 1993 proved that this spacetime admits at least 2 non-isometric extensions. So actually, you can embed it like this in multiple ways that are non-isometric, okay? So these extensions have the same topology. It will be R times S3, and the part that they will be occupying will be the same for the two of them, the part T minus to T plus. So as an illustration, this was the hardest part of preparing the talk, actually. We have here how it will look like. You have this tau initial data set. Here you specify the data, and you evolve it, okay? You go to the future, and you go to the past. This gives you a maximal vacuum Cauchy development, which will be the blue part here, and it will be the tau region. Here you have a Cauchy horizon, which is in the future, and here you have a Cauchy horizon, which is in the past. And then you have this part, that's the extension, that's the NUT extension of the tau region, okay? In this extension that I chose, you can see that you have a lifelike geodesic that goes from the minus infinity all the way to the plus infinity, and another one that wraps up around the horizons and never crosses any of the two horizons, okay? So this is what you actually can have, and this is a kind of pathological behavior. You don't want this to happen, and actually, when you cross the horizon, you have closed time-like curves too, just as I already talked today, okay? Well, so as we were just seeing with these closed time-like curves, these extensions that you get from the MBCD region may fail to satisfy any reasonable causality requirements, okay? So asking for spacetime to be globally hyperbolic, it may be some kind of reasonable requirement. You want to specify the spacetime from an initial data set, basically. Yeah, of course. This is the top data set. This is analytic. You have an analytic metric on S3, and it has a very explicit expression, and you can evolve it, and you get this blue part, which is the tau region. Yeah, the blue part is perfectly good, and you can actually extend it to R times S3. And these extensions, they are two different extensions, two non-isometric extensions, and they occupy the same parts, okay? They are C2, I think, after the boundary. They are analytic? Okay. So he actually wrote the paper, so he knows. I think it has to do with how you choose the gluing in the blue part. How you choose the gluing in the blue part, because for each of these two horizons, you have two ways to actually extend the coordinates, and you have to choose how to extend it, so you see which one of those two geodesics actually crosses the horizon and which one wraps up. So you can actually choose the gluing to be a good gluing here, and another one to be a bad gluing where no geodesic crosses the two horizons. So this will be an extension, and the other one would be something like this. And now here it will wrap up here, and here it will go all the way like this, and then it will wrap up here. So yeah, so yeah, it depends on the gluing. Is it okay? Yeah. Same here. So for any physical theory, you would expect to have some kind of predictability condition, okay? So you kind of expect, as Penrose did, for this behavior that's very pathological, actually, to be a very rare occurrence. And how do we say this? Well, the tau-net picture that you just saw should be non-generic in some sense, okay? So the conjecture by Penrose, the strong cosmic censorship in the vacuum case, and not actually properly stated here because I would have to give a topology or something, is that given an initial data set, the MBCD should generically coincide with the maximal vacuum extensions. So when you can do this because you are specifying very, very specific initial data here. Generically, you should not be able to do this. Okay, so that's the strong cosmic censorship conjecture. So now we know that if we can extend the MBCD, we have to do it through a Cauchy horizon. And so this gives you a possible approach to study the SCC, or the strong cosmic censorship conjecture, which is to study the geometry of these horizons, use the fact that you can extend the MBCD to the other side in some way to obtain some rigidity results for the objects or the spacetimes that contain them. And since it's a rigid result, you should expect them to be non-generic in some sense, okay? So this is why actually Cauchy horizons are important, and the study of geometry makes sense in some way. So from now on, we will assume that this horizon C is compact, and we will work with just one component, the future or the past component. Usually we will just work with the future component. Time reversal gives you the other one. So a theorem by Larson, independently by Bingusi, in 2015, shows that C will be a smooth, totally geodesic null hypersurface, and that means that you have a nowhere null light-like vector field over the horizon that will be tangent to the horizon and also normal to the horizon. Okay, so it will be in the tangent space, but it will annihilate any vector of the tangent space. And it will obey this equation here. Its acceleration will be proportional to itself, and lambda will be a function over the horizon. Okay, so when you finally parameterize the integral curves of this, you get this null geodesics, and these trajectories that obey these geodesics will be the null generators of the horizon. So as this is a null hypersurface, you can restrict the metric of the entire spacetime to this hypersurface, okay? And when you restrict it, since you have a null direction, it will be a degenerate metric. This is a problem because now we will talk about degenerate horizons, but it has nothing to do with the metric. But well, that's what it is. So when we have an horizon, we can actually look at these generators, which are these geodesics that are light-like. And we know that to the past, if we are talking about the future horizon, they are complete, and they will be incomplete just in one direction, maybe incomplete. And we will say that we are having a non-degenerate horizon if there exists at least one incomplete generator. And we will say that it is degenerate if all of its generators are complete, okay? So when you finally parameterize the curves here, they may fail to exist for all future times, or they may not. In case one of them does not fail to exist for all future times, we will say it's non-degenerate. Okay, so when you are studying this sets, the first thing you try to do, or the first thing actually Moncrief and Isenberg tried to do, was to simplify in some way the setup so they could get some results. And the way they did this was to work in an analytic spacetime, okay? If you ask for an analyticity, then you get a lot of results. They actually studied this for a long time. They made very influential papers about this. And they managed to prove a few very interesting things. For example, if you have a non-degenerate Cauchy horizon, so for example, suppose this is a horizon, and you look at the generators, which are the null curves here, you have K, the light-like vector field, and you look at the curves here, then they show that if you are in a non-degenerate situation, then its generators must either close here or densely fill a two-torus, okay? So they either do this and come back, or they start densely filling a two-torus inside a three-manifold. If no generator is dense, then you can actually normalize this vector field K for it to be minus K in acceleration for every time, or 0, okay? This case actually corresponds to non-degenerate Cauchy horizons, and they will live for the future until they reach their affine parameter equal to 1. And this case here corresponds to degenerate, and they will be defined for all futures and future and past times. that there's one incomplete generator. Exactly. It makes them all incomplete with applying parameter 1. This choice of K, let's say. Yeah, exactly. If you have one generator that's incomplete and there are no dense generators, then they are all incomplete. Okay? And even more so, you have actually this equation that's very important, as we will see later. In the case that no generator is dense, so we have this classification, then C must be a Killing horizon. And if C is a compact, non-degenerate null hypersurface in an analytic spacetime, such that all of its generators are closed, then it must actually be a Cauchy horizon. Okay? So you're actually characterizing the geometry of these spacetimes, just knowing what happens in this free manifold, let's say. So now the question will be what you can say in the class of vacuum spacetimes, because analyticity is a very restrictive assumption in many ways. Okay? Usually it works the same way. I mean, results can actually be passed from one to the other, but not the techniques. So that's why we're doing it. So in this case, actually Randall proved in 1998 that compact Cauchy horizons collapse with bounded diameter. So what I mean with this is that if you have C like this, C comes with a degenerate metric H, you will define new metrics here, which will be G sub lambda, and this will be Riemannian metrics. It will be a family of Riemannian metrics that will collapse to the degenerate one when lambda goes to 0, okay? And if you can do this with bounded diameter, then that means that Cauchy horizons do not admit hyperbolic structures, okay? So you're restricting the topology of the horizon just by constructing some auxiliary Riemannian metrics here and seeing how they behave. This is actually a very strong result on the topology. You're just saying all of these manifolds cannot be Cauchy horizons, okay? So what we will do now is to talk about what we obtained, and it will be something that in some way combines the spirit of what Randall did and what Moncrief and Isenberg did. And what I mean by this is we will try to use a K that's adequately defined and Riemannian metrics over the horizon to try to rule out possibilities, okay? So first of all, we will try to specify a definition, that is that the surface gravity of a compact Cauchy horizon can be normalized to a non-zero constant if you have this equation, okay? This is not a trivial matter at all. The analytic case was solved by Isenberg and Moncrief, but you don't always have this, okay? But actually, you have two cases. It's degenerate or not degenerate. And what they proved was that in the degenerate case, something works, and in the non-degenerate case, this works. We did something in the same spirit with Radis in 2021, which is that to show that if we have a non-degenerate smooth compact Cauchy horizon, we can actually do this too. Okay? So the result that Moncrief and Isenberg obtained for the non-degenerate case is also valid for the non-degenerate case in the smooth setting. So we have this vector field K, and we will try to use it in some way to generate new Riemannian metrics and see what we can say. Okay? So the main theorem that we will talk about is this. If we have a non-degenerate compact Cauchy horizon in, say, a smooth vacuum spacetime, then one of the following must hold. Or every generator is closed, or there are only two closed generators and every other generator densely fills a two-torus, or every generator densely fills a two-torus, or every generator densely fills the horizon. Okay? So we can distinguish four very different behaviors here, and they will actually restrict the topology too. When you look at the topology of this, you will say that respectively to cases 1 to 4, in the classification theorem, it will hold that in case 1, every generator is closed, and C will be a Seifert manifold. If there are only two closed generators and every other one densely fills a two-torus, it will be a length space. If every generator densely fills a two-torus, then C will be a T2 bundle over S1. And if every generator is dense in C, then C will be a three-torus T3, sorry. And in this case, not only that, but the MBCD that gives rise to C must be a quotient of the flat Kasner spacetime. So there's only one possible way where one generator can densely fill the horizon. Okay? I think this is the most interesting part of the result, actually, which is that if you have one dense generator, then... Yeah, sure. Yes. The first one is the tau NUT horizon. Cauchy horizons in Gaudi spacetimes actually provide examples of cases 2 and 3. So you can actually find length spaces, and you can actually find T2 bundles over S1 that are examples of these Cauchy horizons. And the last example will be the one we will prove is the only example, which is the flat Kasner spacetime. Okay? So the flat Kasner spacetime is very simple to state. It's just grabbing 0 infinity times L3, and this metric here. It's very similar to the Misner space, if you look at it, but with 2 more variables. So when you look at this metric, you immediately see actually that it has a Cauchy horizon at t equals 0. You cross out this term, and this term does not matter anymore, so you get a degenerate metric. And if you take certain well-constructed irrational quotients, which means to adequately choose the lattice in R3, you can actually construct them so that the geodesics here are dense. Okay? So Isenberg and Moncrief also conjectured in 2018 that this will be the only possibility when one generator is dense. So that's where we took the idea from. So we have a possible topological classification, and we will actually make use of the fact that this is a topological classification. It's not a geometric one in the sense that we don't need the metric to do this. The density does not need the metric, and the classification of T3 does not need the metric, okay? So how we will do this? We will start by taking a nowhere 0 K such that this holds. We know that we can do this. And we will look at the integral curves of this K. These are pre-geodesics, but the integral curves are the null generators when they are finally parametrized, okay? With these integral curves, we will generate an adequate Riemannian metric so that these integral curves are actually the orbits of an isometric action. And then we will have the machinery of Riemannian geometry at our disposal, and we will use it to classify it, and then go back to the Cauchy horizon, okay? So the trick is to grab the K, use the K to construct a Riemannian metric, classify here, go back because we never used the metric to talk about the generators in any way. So first of all, we have to notice that the Cauchy horizon is totally geodesic, and this implies that K is a null symmetry, which means that the lead derivative of the metric over the horizon is 0 when you take it in the direction of K. And the fact that it is totally geodesic also allows us to define this one form, omega K, which will be the product part of K in the direction of the acceleration. And we can do this just because the horizon is totally geodesic, okay? And now we will define this Riemannian metric. So we will just take the degenerate metric over the horizon and then make a product with omega K times omega K. This will actually rule out the possibility of K measuring 0. Now we will measure 1. That's the part that's important here. You can actually prove that this is a Riemannian metric. You have to use the fact that the Cauchy horizon is totally geodesic to see that the lead derivative of this is 0, and this will be because of some properties of the omega K. Omega K is what you call null closed, so when you use Cartan's magic formula, everything closes out. So we have our metric, and we have our vector field K, and we will use just the machinery from Riemannian isometric actions to see what we can do, okay? So now we have K acting on a Riemannian manifold, and it will induce an isometric action of R, and by compactness, this flow is well defined for all C in R, okay? Since C is a compact manifold, this flow will be defined for all times. And so the diffeomorphisms that are just taking a P and flowing in a time set will form an abelian connected in one-dimensional subgroup of the isometry group, which we will denote by I. So we're just saying, now we have a Killing vector field for a Riemannian manifold. We can flow by this Killing vector field, and this is just a one-parameter family that's defined for all times. There's a very powerful result, a very classical one, I think it's from 1931, by Myers and Stirrod, that says that if you have a compact manifold, a compact Riemannian manifold, the isometry group is actually a compact Lie group. Okay? And when you look at the group action G that is given by K, you see that it is an abelian and connected subgroup of a compact Lie group. It's abelian trivially because you're just like moving at time x1 and then at time x2, which is the same than moving at time x2 and then x1. So now its closure must be an abelian connected and compact Lie subgroup by a theorem of Cartan. Okay, so we just reduced the problem of studying this K to studying an isometric action, and that action actually generates a compact Lie subgroup of the group of isometries. The compact Lie subgroups that are abelian and connected are completely classified, and they must be tori, or points, but they can't be points because the vector field K is nowhere null. So you know that the closure of G must be isomorphic to a torus for some n. If you know that this action is transitive, then you can prove that when you take a point P and you flow it by this action, its image is an embedded flat torus for some dimension n, m lesser or equal than n. Okay? This is actually quite simple to prove, but you're just saying that since you have a compact, connected abelian group acting, first of all, you can see that the isotropy groups are all the same for the orbit, and then from there, it's basically everything done. And now you can relate the orbits of the closure with the orbits of the first group. How? Well, when you want to look at the orbits of the closure, you can just take the closure of the orbit. Okay? So this is what we wanted to see. We had G, which was the action by K, and we've just flowed by G. Then we take a closure, and now we know that that's the same than acting over the closure on P. Okay? So if we combine both results, we know that the orbits here will be embedded flat tori for some m. So for each point, you look at the action of the Killing vector field and you take the closure, and it will be a torus. It can be an S1, it can be a T2, it can be a T3, but it will be a torus. Okay? Now comes the less known part, let's say, which is that when you have an action like this, you have something that's called the principal orbit, which is that this is not exactly a definition, but it gets close. You can look at the orbits that have maximal dimension among the orbits of the closure. So you look at the action, some orbits will have dimension 1, some will have dimension 2, some will have dimension 3, maybe. And you just take the ones that have greatest dimension of them all. If you denote by C print, I guess, the principal set, which are the points that belong in a principal orbit, there's a very powerful theorem here that says that the points belonging in a principal orbit are open and dense on the manifold. So you basically saturate this manifold by points that are as maximal as they can be when you flow them by the action. And not only that, but when you quotient it by the action, you see that in the quotient here, that may or may not be a manifold, you have a connected manifold. So this lives here, but this is a connected manifold. So this simplifies everything, because when you take a quotient of a manifold, which is three-dimensional, you can only get dimension 3, 2, or 1. And now you have to study that, okay? So you apply the result. And first you say that principal orbits must be tori of dimension 1, 2, or 3, because you know that every orbit is a tori. Now you go to the quotient space. You say, if the principal orbits are one-dimensional, then every orbit will be one-dimensional, and they will all be embedded circles, and every generator must be closed. This gives you case 1. If you have principal orbits that are two-dimensional, you can study the quotient structure, okay? This takes some work, but you can see that the structure will be either 0, 1 closed or T1. If you are T1, well, you are a T2 bundle over S1. If you are 0, 1 closed, then you have tori in the open 0, 1, and then S1s at the boundaries, okay? And if the principal orbit is three-dimensional, when you take the set, you know that it is a dense and connected manifold over the quotient, and so every orbit must be dense. And this gives you case 4, and it shows you that C is T3 actually. And it's flat because its embedded image was flat. When you look at this quotient, this actually simplifies a lot, and it allows you to show that cases 1, 2, and 3 follow, okay? What I mean is, when you look at the structure, you see that either you were a Seifert manifold, or you were a length space, or you were a T2 bundle over S1. So, we are now left to proving with the fact that the MBCD that gives you a dense generator is the flat Kasner space. But for this, we have a very powerful characterization. I don't know who this is from, actually. I read it from a Ringström's book, and it wasn't cited there, so I'm not sure. But you have this characterization. If you have T3, an initial data set, and it is translation invariant, and its MBCD admits a compact Cauchy horizon, then the MBCD must be a quotient of the flat Kasner spacetime, okay? So, what this shows is that if we want to show that if we have a dense generator, we come from the flat Kasner spacetime, then we just have to build a good initial data set, basically. So we will do this as follows. Let me... Yeah. Really? Oh. Yeah. So, but we have now this machinery from Peterson. So first you start here. You have this torus, T3, and you know that you have a dense generator here. Okay? And over T3, you have this vector field K. And you know that nabla K equals minus K. Now we use this fact. This is a Cauchy horizon, and then you have the MBCD part here. So you have this good part that you can predict from an initial data set. And Peterson-Rax actually proved that if you have this condition, you can extend this vector field K for it to be a killing vector field over the MBCD. Okay, so you have this normalized vector field K over the horizon, and you can actually pull it down to the entire MBCD. In this part of the manifold, it will be actually a space-like. So you pull it down, first of all. You just grab this K, you pull it down. Now you flow by a light-like geodesic here that you have to carefully choose for every point, and you flow here, and you get a diffeomorphism here by flowing back in time to the MBCD region. You get a diffeomorphism with a Cauchy hypersurface and a Riemannian metric. And you know that this vector field K that you extended is actually tangent to this Cauchy hypersurface. Okay? This is not trivial, you have to prove it, but you can do it. And by construction, you see that if you have a dense orbit here, when you flow, you have a dense orbit here. How is this by construction? Well, you choose the L carefully, so you flow by L. You choose the L carefully so that the flow of L and the flow of K commute. So if you are dense here, you can go back, go down, and this is a euphemerism. So if you are dense on the top, you will be dense on the bottom. So now what you constructed is a vector field K. So now you have a vector field K here that has dense orbits over T3, and now the metric here will be actually Riemannian, because you are in the space-like part, and this is a Cauchy hypersurface, okay? So you started from a Cauchy horizon, you took it down, maybe it just bent a little bit. Now you have a Riemannian metric here, and the vector field K is actually tangent here. But it's still a Killing vector field of the entire MBCD, so it will be actually generate an isometry group, and it has to be a T3 isometry group because it's still dense, okay? Since it acts isometrically and transitively over sigma g, it must be a flat torus, and since it comes from a space-time symmetry, the extrinsic curvature will be invariant by the action of the closure of the isometry group, and now you have a translation invariant initial dataset that admits a Cauchy horizon, so you use the characterization and you say this is flat custom space. Okay? So finally, I want to talk about some recent progress and open problems. So first of all, it is now known that vacuum compact Cauchy horizons are actually Killing horizons. This is a very long series of works, some by Friedrich Ratz and Wald, then by Petersen and Ratz, and by Petersen, and finally with this vector field K for the vacuum case. And we can actually ask this question. Since we know that this is a Killing horizon, can we use this fact to improve the classification in the case where no orbit is dense? Can we say something else about the topology, or from which spacetimes these Cauchy horizons that are either length space or Seifert manifolds or T2 bundles over S1 arise? Because here I never used the fact that this was a Killing horizon. I just used this vector field K. Second question. If you know that every generator is complete, that's the degenerate case, what happens in the degenerate case? Well, there's a conjecture by Isenberg and Moncrief in their last paper in 2020, I think, that there are no compact degenerate Cauchy horizons. So they now conjecture that there exist no compact degenerate Cauchy horizons. And finally, we can ask what happens in the vacuum case. And thanks to the work by Minguzi and Gurriaran, where they actually extended this to the case of the dominant energy condition, and they found a new proof for the vacuum case. We also know that this classification holds under the dominant energy condition. So any Cauchy horizon in, say, a dominant energy condition spacetime will behave the same way. So can we relax this condition even further? Can we ask for even less than the dominant energy condition? Maybe, or we can ask things about the regularity too. Can we ask for less regularity in the metric? Maybe not smooth, but I don't know, CK for some K. I don't know, because you have the Meyer-Steenrod theorem, but maybe you can. I don't know. So that was all, and thank you very much. Yeah, sure.
We have a compact program. Would Cauchy run compact?
I don't know the answer. I guess that I would say that having a compact Cauchy horizon is a very special case of Cauchy horizon, actually, but you have to start somewhere, basically. So I would say that maybe Ettore or Piotr can tell you something else about it. Yeah. 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 I mean, it's just a way to start somewhere, let's say. So they first just studied the compact case. They had to assume an analyticity too to use the Cauchy-Skaya theorems. And now we are just trying to relax those. We've finally managed to relax the smooth case. But I don't know what happens in the non-compact case, sadly.